All right, y'all, what's up? So today is January 20th. Whew. 2-year anniversary of Google layoffs. I'll talk about that in another video. Anyways, today we are about to go live. Well, we are live, but we're about to start practicing proofs. We're about to start practicing and introducing a theory of proof writing. This book has been universally loved and recommended just nonstop. If you search it on the internet, everybody loves this book and recommends it. People have dropped in the chat and said, oh yeah, that book is excellent. So I'm excited to see it. This is almost like a math reaction channel where I'm reacting to books. So yeah, I'm excited. So this is a slight change in the number theory series. So right now I have 3 series, 1 per week, number theory, linear algebra, and calculus. I think it makes sense because calculus and linear algebra can both be studied in a very applied fashion and just computational and just, solve engineering problems. Number theory, you just can't. Number theory is about proofs. Number theory is mathematics for mathematics' sake, for the most part. And so I think it makes sense to teach and introduce proof theory in the number theory series. So let me know what you think. I think that the series will be retitled Number Theory / Proofs. Or Number Theory and Proofs, or something like that. So we're going to work through this book together. Over time, we might either split out a separate foundations series, maybe, or I think more likely we'll just keep adding more and more foundations, like logic. We could just add logic into the number theory and foundations series. This stuff is starting to move away from number theory, but especially category theory is critical to understanding modern number theory. None of these books are number theory. I don't know what I'm doing. But anyways, and then there's some beautiful, beautiful connections between logic and number theory, and especially with regards to Gödel's incompleteness theorems. So yesterday in yesterday's video, I defined the roadmap and some goals. What are the goals of this channel? And I stated a couple of the goals for the number theory series. I want to climb Mount Everest toward understanding Fermat's last theorem. Full stop. That's why my little channel avatar is Fermat's last theorem. I want to climb that mountain. There's a lot of side quests along the way, and a lot of beautiful results that we're going to see along the way, including quadratic reciprocity. That is one of the goals. Similar to quadratic reciprocity, I want to make my way toward Gödel's incompleteness theorem. I want to understand that and have, in a hobbyist, shoddy fashion, taught all of the theorems leading to Gödel's incompleteness theorems. And then, I'm not going to pause and just list every single beautiful result along the way, but main goal for Fermat's last theorem, at least in the number theory series. I don't know what the goal is of linear algebra and calculus, probably to understand or be able to contribute or something about ML, blah, 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 machine learning, artificial intelligence for linear algebra. Maybe it's probability and understanding statistics and probability, really understanding measure theory, which you need to understand in order to study probability. I feel like that might be the goal of calculus. And it's very authentic because these are genuinely topics that I want to learn for myself. This is pretty hardcore. This is math major talk right now. This is somebody who goes to grad school studies this stuff. But my handle is the math hobbyist, and it's true. I don't think I want to go to grad school. I just want to study this stuff because it's beautiful and because it's fun, and I think it's possible. I think I can understand Fermat's last theorem as a hobbyist. And even if we can't get there, it's worth a shot, right? We're going to have fun along the way. So stay tuned. Thank you for watching. Let's just jump into it, shall we? I don't have any questions, I don't think. Nobody had any comments other than a couple of nice supportive comments. Somebody said, this channel is going to blow up in the future. Congrats in advance. And I was like, thank you. That's nice. So thank you to the person who said that. I forgot your name. And yeah, I was thinking of maybe playing a guitar song during a break in the middle of this video, but I have this freaking annoying hair that's stuck in my finger, so I don't know if we'll do the guitar song today. Maybe we will anyways. We'll see. Alright, so proofs. A lot of people struggle with proofs. A lot of people find them difficult, challenging. It is a huge gap. It's something that separates the engineers from the mathematicians, let's say. Like, you can get a math minor by, you can usually get a math minor by doing like the calculus series, linear algebra, differential equations, and you can feel like you know math, you know what math is like. If you want to be a math major, you need to study proofs. You need to study abstract algebra, you need to study real analysis, and those courses are what really separate a lot of people from, I don't know, it's like computation and the really useful sides of math, like whatever, being able to calculate how far you can throw a baseball or something. Proofs separate engineering math from pure math, from math as an art form, math as a logical game. Like, to me, capital M mathematics is proof-based math. Yeah, I don't know where else I'm going with that. Mathematics is, like, to me, mathematics is very close to philosophy. It is a logical pursuit in and of itself that is beautiful and kind of useful sometimes, but mathematicians don't study it because it's useful. Mathematicians study it because it's wonderful and it's beautiful and it's fun. Kind of like philosophy, I think. It can find applications, but that's separate. Like, applied math and applied philosophy, it's in a sense a separate thing. It's a separate degree often, or at least a separate focus path if you study mathematics. My university offered a Bachelor of Science in Math as well as a Bachelor of Arts in Math. I finished the Bachelor of Science, but really I took all the classes for both of them. And I just think that there's a real argument that mathematics is an art form. And that's one of the main things I want to convey with this channel. The beginning of these videos are kind of like a little vlog, a little just talking to the camera, a little vlog that might be interesting for people who want to follow on my journey. And then we're going to switch gears into a practice session. So I'm just live learning, live practicing, solving problems, teaching theorems, relaying work that I've done privately recently, and just hanging out, just chatting and hanging out with folks, which is also valuable. So yeah, proofs are tough. Like, I just want to make that clear. Proofs are tough for a lot of people. They just are. doesn't mean that you shouldn't do them. They're so much fun. They're beautiful. They're lovely. And if you really want to study advanced math, one thing I want to say is like mathematics is not about, generally it's not about finding evidence that something is true, and like we've seen that something is true in a bunch of cases, and all of our results, all of our scientific tests, we haven't been able to disqualify this hypothesis, therefore it's probably true. Like, no, that's not how mathematics works. There are mathematical statements, theorems, conjectures that we have seen are true for an absurd number. I don't know, a Googleplex number of cases. That's not actually true, but like some ridiculous number of cases, millions of cases or something. But we still don't call that problem solved because it turns out that there are infinite numbers. So just because you've calculated and seen that some claim is true for a million or a quadrillion cases, that's nothing compared to the size of infinity. Infinity is, just it swamps the number of like quadrillion. Quadrillion is nothing. Quadrillion is zero compared to infinity. And there have in real life, there actually have been conjectures that we've seen are true for whatever, a million, a quadrillion cases. And then we've proved that we don't know when, but at some point there will be a counterexample. Somewhere, way out in the vastness of infinity, at some point there will be a counterexample to this claim. I don't remember what it was, but there are examples of things that it looks like there was a lot of scientific evidence that this thing would be true, that this claim, this proposition would be true, and then turns out it's not, which is amazing and beautiful. So mathematics needs a level of certainty and truthiness to a mathematical claim, and it makes it very unique amongst all of the sciences, amongst the sciences. It's very unique in the level of confidence and the level of certainty that mathematics shoots for and aims for. That's the simplified ideal world, but then in truth, in practice, especially recently, mathematics has been getting so complex that there are contradictions popping up in papers. Two papers are contradicting each other. There have been mistakes that have happened in the past leading to like epsilon delta definitions, formalization of math in the past. We're running into some problems like that today. I want to get involved with that work. There's some new work being done right now to reformulate mathematics in even more firm, rigorous grounds. If you're curious, search for a talk about lean by Kevin Buzzard, Buzzard. I can nerd out about that stuff, but my point is that the level of certainty that mathematics shoots for is 100% certainty. Like 99.9 whatever is not enough. And that makes it so cool and beautiful to me. It's like, I don't know if we live in a simulation. Like, I think that I've seen that some scientists put it at 50-50, like a coin flip, that we might live in a simulation. I don't know. I mean, that goes way back to Descartes. I think, therefore I am. In that same, in the Meditations, Descartes imagined he used mathematical reasoning. Like, I think, therefore I am. That was Descartes applying mathematical reasoning and mathematical logic, the same stuff that we're about to study today, to try to prove the existence of the real world, and for him also to prove the existence of God. He wanted to prove mathematically the existence of God. And so he was applying the method of mathematical proof by contradiction, which we will learn in this series. And the idea is, if you can come up with a possible counterexample, it doesn't matter how absurd the counterexample is, as long as you have a counterexample, then you kind of have a contradiction. And so you have to remove that belief. And okay, like, so for Descartes, first it was like, how do I know that reasoning exists, or that I'm a rational being? I forget exactly how this works. But the second one is like, how, like, I claim that there is an outside world in which I live in, and then the counterexample is like, yeah, but you've dreamed of worlds before. You've had very vivid dreams. How do you know that you're not in a dream right now? How do you know that you're not living in a very complex dream? You've had dreams in which you've had dreams. You've had, like, those inception recursive dreams before. So how do you know you're not in one of those? And so for him, he was like, okay, I can't even assume that there is an external world. The simplest axiom that Descartes was able to come to was, I think, therefore I am. I think, therefore something is happening. I am thinking right now, and I can't imagine any way to disprove that. Something is happening. I am thinking now. That is the bedrock of Descartes' mathematical philosophy. And then he tries to build up from there, from that axiom, a theory of the existence of the world, and then existence of God, and things like that. And then other philosophers came in and challenged and pointed out holes in his argument, and then it's a beautiful war between the rationalists and the empiricists, following up with Kant, kind of answering both of them, and that's a story for another day. But what we're going to be doing is something very similar. It's just that in philosophy, we try to... I did study a philosophy minor, by the way. In philosophy, we try to apply mathematical and analytical reasoning to the real world. And you try to, at least in Western philosophy, it's very based in logic. Like, this course that I took was cross-listed from the philosophy department and the mathematics department. So philosophy is very much grounded in logic, and you try to apply logic to constructing theory about the world. In mathematics, it's kind of like a subset of philosophy in which the only claims that we're really trying to study and understand are numbers and mathematical statements. Not just numbers, but things that live in the world of mathematics. And so number theory is the beginning of all of that. Number theory is, in a sense, the simplest of mathematics. And it's the most natural. It's literally the natural numbers. Like, I have one thingamabob right here that I'm holding. I have 5 books here on my table. Counting. Like, it's hard to believe that counting doesn't exist in the real world. It's hard to imagine that if I put 5 acorns here and 4 acorns here, and then I fill in an acorn... If I have 4 rows, 4 rows of 5 acorns, that I don't get the multiplication 5 times 4. That is a very natural beginning of mathematics, and that's why we're doing a number theory entire series that takes that to a limit. But yeah, like, where am I going with that? Proof is, mathematics is about proof and certainty. Euclid's Elements is the most successful mathematics book of all time, and it is a masterwork, a beautiful, beautiful book all about mathematical proof. It was written way before we had like Arabic numerals, the numerals that we all use. But it was all mathematical arguments about starting with shapes like circles and the intersection of circles, or Pythagorean's theorem, triangles, whatever. Lots of stuff. But the way that book presented mathematics and shaped mathematics for thousands of years now, or at least 1,000 years, I don't know. Yeah, thousands, right? I have no idea. When was the Elements published? Thousands of years ago. The structure of it is what mathematics has always followed. It's that you come to those ground truths, the bedrock of beliefs, like the fact that you can have a number, and that anytime you have a number, you can add one number to it. Like, we can all agree on that as the rules of the game. Like, let's all just agree and assume that you can always add 1 to any number. Luna, chill out. My kitty cat. My kitty. Say hello to my beautiful baby cat. So let's all assume, let's all agree that yes, you can add 1 to any number. That the number 0 exists, and that you can always add 1 to a number. From there, from that assumption, then you can define the concept of the number 1, or the number 2, or the number 3. The number 3 is 0 plus 1 plus 1 plus 1, right? So that is, in a sense, like one of the axioms of piano arithmetic. Most people have experienced axiomatic mathematics in context of geometry, at least in the United States, and really for thousands of years now, ever since Euclid. Geometry has always been taught as this, as like the example for proofs, like the example for mathematical arguments, of doing axiomatic proof-based mathematics. And I personally think that's wrong. I don't think it's wrong. I wish that course in the United States that you take when you're in middle school or high school or whenever, I wish it were teaching geometry and number theory at the same time. I wish that it wasn't like this idea that, like proof-based math is only about shapes and geometry, and I don't like geometry. I don't care about shapes. I'm not an artist. I don't like painting and drawing. I'm not a visual person. For me, like I'm actually speaking about myself. I was not that interested in geometry when I took geometry in middle school. I was like, it's not for me, and I don't like this like really structured, like formal table-based proofs. It's just possible. Like, my teacher was fantastic, but I just think that the curriculum isn't really built the right way to show the beauty of mathematics in other types of mathematical arguments. I think I personally would have been more interested in seeing the paragraph-based mathematics. Like, when you study more and more mathematics, it stops looking like a bunch of problems and exercises, and it starts looking more and more like paragraphs and a story and just like written out paragraphs of math. I wish I had seen that. In Euclid's Elements, in that book that Euclid wrote, that what has been the cornerstone of mathematics education for thousands of years now, he proved a lot of number theory. He proved a lot of ideas in number theory. Greatest common divisor, like there's a really beautiful algorithm for computing the greatest common divisor of two numbers that is incredible from Euclid's Elements. The Euclidean algorithm is what it's called. And Euclid proved that there are infinitely many primes, which I think we could do today. Why not? Today would be fun to do that. He proved lots of facts about numbers, about mathematics, about number theory, the definition of primes, for example. I wish that we taught proofs with number theory. Because with geometry, you're kind of mixing two different... You're mixing two different types of learnings at once. On the one side, you're learning all these formulas for the area of a square and maybe trigonometry functions like sine and cosine and stuff. And you're learning all of these theorems about geometry, about shapes and complementary, supplementary angles, and things like that. You're learning like actual new math, and at the same time you're learning mathematical reasoning and mathematical arguments. I think it's always better to learn one thing at a time. Those are two very separate skills. And to this day, I still don't care that much about planar Euclidean geometry. I just don't care. I'm way more interested in numbers. And I think it would be so cool to see a high school class teaching mathematical proofs. Maybe you do start with a table-based method because it's really nice and structured and easy for people to learn, but then try to move over to paragraphs and actually writing out a mathematical argument in number theory, which I think is cool because then it would be like, okay, you're in 10th grade, you're in middle school or high school or whatever that is. Now we're going to learn about mathematical proofs and mathematical reasoning. And guess what? The math is going to get a lot simpler. Do you remember when you were in second grade and you learned about addition? Or, no, you probably learned addition in like kindergarten, but like in second grade you learned about multiplication and maybe you learned about prime numbers somewhere around then. I don't remember. Like, and at some point, maybe, who knows, in fifth grade, you learned about the greatest common divisor about two numbers. And at some point, you use that in order to add and subtract fractions with different denominators. Well, you need to find a least common multiple and greatest common divisor, very closely related. I think that would be so cool to see intro to mathematical reasoning with number theory, because it's familiar to everybody, and then you could be learning just mathematical arguments and reasoning in itself, feeling like, oh yeah, I liked this kind of math back when I was in elementary school. This reminds me of when I was a kid. learning multiplication and divisibility and like the long division algorithm. So I guess that's what we're doing here. I guess we're going to try to create what that would look like, learning proofs in context of number theory. Even at my school, at my university, you had to take, for us, intro to proofs was abstract algebra. We had a combined intro to abstract algebra and proofs. And then that course was a prerequisite to taking number theory. So you had to have already learned proofs and truth tables and things like that before you could take number theory. I just think it would be cool to see number theory used as the motivation for intro to proofs. So there's a little rant. I hope you enjoyed it. I hope that gives a little bit of motivation and flavor as we switch over to the iPad. I'll show a few of the problems that we might start taking a look at and talk just a little bit more about the book that we're about to work with. All right, so this is an old iPad. Here we go. Okay, so how to prove it. The introduction. I haven't read it. I might skim through it and relay some of it, but here are some of the problems that we're going to tackle in the introduction. Factor this number into a product of two smaller positive integers. Cool. Okay, 2 to the 15 minus 1 equals that. Factor it into two smaller integers. So we all probably remember that factoring a number like 15, or you know what, let's go with 35. That's a better one. 35 is 5 times 7, right? So what we're going to look for is a number such that 2 to the 15 minus 1 is the multiplication of two smaller integers. All right, so that's still kind of computational. But then we're like learning to like read these mathematical sentences, like find an integer x such that x is smaller than that big number. Then now the big number is in the exponent, and that thing is divisible by x. I actually don't know how to do this. I'll have to read the section. That sounds cool. That sounds really cool. But we will... Interesting. Yeah, that sounds really cool. All right, 0.2. Make some conjectures about the values of n for which 3 to the n minus 1 is prime, or the values of n for which that is prime. These look like cool problems. I don't know. So we'll start with a table, and we'll take a look at figure 1.1. The proof of theorem 3 gives a method for finding a prime number different from any in a given list of prime numbers. Wonderful. So this is what I wanted to show as a motivation for proofs. I don't need to read theorem 3. I'm pretty sure I know what that's referring to, and I will try to give my own version before we just write down Velleman's. That is Euclid's proof of the infinitude of primes. The Greek mathematicians did not like the concept of infinity, so he didn't say that there are infinitely many primes, but he said in any list of primes you can find another one. That's like slightly different. That's just ever so slightly different, but it is still kind of the same idea. Okay, and then so just reading these problems, we can get a sense of what the introduction section is like. Find 5 consecutive integers that are not prime. So all of this, these statements that we're talking about, this is number theory. We're talking about prime numbers, infinitude of primes, etc. So I think it's cool that Velleman is teaching proofs with number theory examples. I think proofs make more sense in number theory than in geometry. All right, so there's an introduction. I thought that this one is cool. I always love it whenever there's an exercise that defines a new concept, like the amicable, friendly numbers or something. So maybe we'll tackle that today. I doubt it. But then in section 1.1, we will talk about deductive reasoning and logical connectives. Analyze the logical forms of the following statements. So I said that mathematics is based in logic. Like, in a sense, philosophical logic is an underpinning beneath math. And so here we're learning about logic a bit. We'll have either a reading assignment or homework problems, but we won't have both homework problems and a test. You won't go skiing, or you will, and there won't be any snow. Square root of 7 is not less than or equal to 2. Right? Analyze the logical form of the following. Either John and Bill are both telling the truth, or neither of them is. Blah, blah, blah. Analyze more logical forms. Analyze more logical forms. 115. So here is where Velleman switches the exercises to symbolic logic of showing like the symbols for and, or, not, etc. And we'll learn a bit about that. Let P stand for the statement, I will buy the pants, and S for the statement, I will buy the shirt. What English sentences are represented by the following formulas? So pause the video at any point if you want to try to tackle these problems on your own. I haven't written down those yet. And then how to prove it 1.2, sentential logic truth tables. Make truth tables for the following formulas. Make truth tables for the following formulas. And then these. So in this exercise, we will use the symbol plus to mean exclusive or. In other words, P plus Q means P or Q, but not both. Make a truth table for that. Find a formula that expresses exclusive or in terms of the simpler connectives. Justify your answer with a truth table. So I think that's about, that's definitely more than we're going to do today, I think. But yeah, I hope that gives a little bit of flavor and stuff. I think what I'll do is I'll copy things over as we move on. All right, so what is today? Day 5? Relearning. How's it going, everybody? I see that there's a couple people in the chat. Say hello. How's your day going? What kind of math are you studying? Is this your first time seeing number theory and proofs, or are you reviewing it? How do you like the channel so far? All right, I am the math hobbyist, and today is the 20th. Cool. All right, so today we are going to introduce proofs. So a proof always has a claim. A claim can be called a theorem. Theorems are the theorems are the baddies. Theorems are the ones that you want. They're the ones that are the biggest results. They're the big results that are that you're working toward. The most beautiful results, most beautiful mathematics. This is just pure human right now. This is just us talking about, like, I like this one more than this one. Aesthetically, a theorem is prettier and more beautiful than a lemma. A lemma is kind of a tool that you build in order to prove a theorem. Like, quite literally, a lemma is a stepping stone to a theorem. But a lot of the time, you could consider a lemma a theorem on its own. Like, that, this is just arbitrary. And then a kind of a follow-up or a I can't spell. All right. Corollary. A lemma is a stepping stone. A theorem is, I don't know, a major result. And a corollary is a follow-up, like a layup. So lemmas are a stepping stone to theorems, and then corollaries are easy results after a theorem. Yeah, I think that that's accurate to say. But then again, all of this is humans just giving terms for, in some rough sense, this one is more important than this one. There are a lot of mathematical facts that we prove just as stepping stones to something more interesting. So, I wanted to define theorem before I wrote it down. Theorem by Euclid. There are infinitely many primes. Okay, so we need our definitions. Do we all understand what infinite means? Do we all understand what prime means? All right, so infinitely many. What does infinitely many mean? Well, the Greek mathematicians really didn't like doing math with infinite. To them, they preferred this equivalent other form that is, and in a sense, these are definitions. Infinitely many, that means that I don't know, there is no list of all of whatever the thing is. You can't list them all and write them all down in an order, like 1 through n. Also known as for any list Ti, you can find another Ti plus 1 that is not in the original list that you had. So I'm playing a little fast and loose with notation that I haven't defined yet, but I hope that you understand what I mean. If you list a bunch of things, that there is another one that's not in that list that you just wrote down. So this is really what Euclid showed. Like, for any list of primes, you can find another one that's not in the list. All right, so that's what we mean by infinitely many. What do we mean by primes? By prime. A number prime if the only factors such that P is a multiplication of two numbers are A equal 1 and B equal to P, where 1 is less than or equal to A, less than or equal to B, less than or equal to P. Okay? So if we have two numbers that multiply to equal another number, like you just gave me a bunch of acorns and I want to line them up in neat rows, neat organized rows, that would be A acorns per row and B rows in total. If the only way to organize those acorns are in neatly is just one each and P rows in total, like the only way that I can organize those in a nice neat rectangle is in a long line. That's a bunch of metaphors, and I'm trying to say that so that I connect it to something in the real world which we can take as an axiom. Like the idea of multiplication we can take as an axiom. It exists, and that'll be our starting point. Like multiplication and factorization we're taking as a mutually agreed upon starting point. So this is, I think I didn't miss anything. I think that this is a good definition of what prime means, but it relies on simpler ideas. It relies on multiplication. It also relies on the idea of an integer or a number, a counting number. And I suppose it also relies on ordering. Like if you can list, if I give you two numbers, can you order them and say that this one is less than or equal to this other one? And it probably also relies on the concept of only. Like, there's only one way to write down this number. Like, in some sense, like the idea of uniqueness is important. And that all of these things, the definition of prime relies on these simpler truths that we all agree on. And then if you want to be an unemployed philosopher, then you can argue all day about, but what if uniqueness doesn't exist? And things like that. All right, so here's a theorem. I think I've defined everything that's necessary for it. Now, let's see what a proof could look like. And let's see if I get this right. Proof by a hobbyist. Okay, so is it reductio al absurdum? Reductio a absurdum? Something like that. So, also known as proof by contradiction. Okay, so we will argue that this is true because if it weren't true, that would be crazy. That would be weird. That would just be that's not true. Right? Like we're going to show that the alternative is not true. That the alternative is dumb and you're a dummy if you believe the opposite. So, suppose that the alternative, as I said here, suppose that there are a finite list of primes. Say P, the list Pi, as I wrote over here, infinitely many depends on building a list. So suppose that there is a list T1 through Tn of things, in this case primes. So I'm going to use the nice symbol and notation P to mean primes, but I could use anything here. Say that there are a finite list of primes. Say the list is P1, P2, ... Pn. If this list was every single prime, then we run into this absurdity. Then consider the new number I don't know, n. What happens if we multiplied every prime together and then added 1? By definition of primes, also known as there is no, how does this go? Well, let's see. By definition of primes, and I'm going to say the fundamental theorem of arithmetic or division. Yeah, why don't we say division or factoring? Division. N is not divisible by any of the given primes. N divided by Pi has remainder 1 for any Pi. Therefore, there must be another Therefore, there must be another prime that divides n. Because n is greater than n is greater than every prime in the list, and so it is, we assumed, and so it is not prime. There must be another prime that divides n because n is greater than every prime in our list. So, and we assumed that this list was every single prime that has ever existed. So n cannot be prime. By definition of not prime, n equals AB for some A that is not 1 and B that is not n. But yeah. A and B are not any of the primes that we've already listed because A and B are not any of the primes that we've listed because if you divided n by any of those primes, it would have remainder 1. So there must be another prime so there must be another prime that's not in the list. Draw this little box, or we say QED, whenever we want to drop the mic and say, boom, done, we did it, we finished this proof. I'll also say every now and then, boom, like that. I think that was okay. I think it was a little wordy. I think I claimed that this is a proof by contradiction, but we didn't actually need to use that. Like, you can view it from that lens and you can phrase it as a contradiction. Like, there's another prime not in the list which contradicts the idea that we've written down every prime. But you can just reframe this ever so slightly that just says, take any set of primes, then I can find you another prime that's not in that list. That's a construction. That's like a proof by construction, and it doesn't, I think self-criticizing right now, I tried to claim that this is a proof by contradiction, but it could just be slightly reworded so that I don't need to rely on that concept. Like, the important thing is that we constructed a new number. We constructed that number which will give us a new prime that's not in that list. Yeah, all right, so now let's see, how did Velleman write this down? And this is style. This is style. Many different books will write down a proof differently and fill in more details or less details, and style matters, y'all. Style matters a lot. Don't go crazy with style guides and linters. Like, style guides are very useful, but don't go crazy with them. It's possible to write down two separate valid ways to write down a proof, and they can both be good. It's possible to format your code in two different ways and for them both to be good and valid. There's my rant on style guides. Hey, Old Man Silencer, good morning, man. How are you? I'm trying to give my own practice proof of Euclid's theorem that there are infinitely many primes. You've seen this, right? How's it going, man? How are you? So, we constructed a new number which is immediately going to give us another prime. Here's a gotcha. A lot of people will claim gotcha. Fools, freshmen, people will say n is prime. But that's not necessarily true. It takes a while to come up with an example, but eventually you can come up with an example where n is a factor of two numbers where both a is not in the list and b is not in the list. That is possible. I don't remember how long the list of primes needs to be, but we're going to get some cool exercises. Oops, I forgot about 11. We're going to get some cool exercises where we can use this machine to actually build us new primes, which is super cool. And this is one thing where a proof by construction is in some real sense more valuable and more useful and more elegant, more prettier, better, whatever word you want to use. It is better because it can you can actually run some sort of algorithm usually, or you can come up with another example. Whereas, speaking of proofs there's proofs by contradiction, there's proofs contradiction. In a previous video, I introduced proofs by induction, proofs by mathematical induction, and then there's like proof by construction. I think that it's okay to call it proof by construction. Construction is in some sense better than the others. These are kind of less elegant, usually less elegant. But I'm immediately going to say that's not true. Elegance is this human concept that is where mathematics is an art, and it would be a foolish attempt to try to define what mathematical elegance is. That is the sort of thing that ChatGPT is never going to be able to understand. Like, mark my words, 20 years from now, we will still say that ChatGPT does not understand mathematical elegance. It's going to get close. It's going to get really good. It might be hard to tell. It might be really, really hard to tell if it understands elegance. But no matter what, I think aesthetics and elegance and these kinds of ideas that you can't define and write a style guide around. That's the sort of stuff that humans have that ChatGPT can't get. All right, so let me catch up on chat. I'm well. Long time ago, you've seen proofs. Haven't thought about proofs seriously in 10 years. Nice. Most people haven't. Proofs are gorgeous and so much fun. That's what this channel is about. Proof by construction is what Euclid did. Exactly. Yeah. Euclid did exactly this as well. I know that this is the basic idea of Euclid. Like, don't get me wrong. I said this is proof by the math hobbyist. No, this is the proof by Euclid. It's my relaying of Euclid's proof. I think it might take more than 20 years, but I do think it might get there eventually. I think it's a categorical separate realm. I don't think ChatGPT is... I don't know. I mean, it's a philosophical argument, but I think that there's something innately human in an evaluation of beauty that don't get me wrong, ChatGPT is going to get good at it in terms of like get the job done. Like ChatGPT is going to produce beautiful movies soon, or short videos or funny cat clips or whatever. But it is not itself going to understand beauty anytime soon or ever. I don't think, like, it's going to have its own conception of what beauty is and its own different realm of aesthetics, and maybe it's equally valid. Maybe it is its own interesting, equally valid realm and philosophy of aesthetics. That sounds so cool. That would be like a philosophy dissertation or something. We might have to crack into this book at some point, y'all. We might have to crack open this book in order to build our theory of ChatGPT's aesthetic theory. But yeah, like, oops. When I say theory, the assistant pops up. Yeah, aesthetics. I think that that's just an innately human concept that is hard to write down in a style guide. Impossible to. And aesthetics and beauty are important. Like, ChatGPT is going to be fantastic at producing lean proofs that are indecipherable and prove things like the Riemann hypothesis. It's going to be fantastic at doing math in terms of giving us a certainty that some statement is true. But, like, I think most mathematicians don't care about the math statement itself. They care about the reasons that something is true. They care about the logical argument and how does that argument, can you twist that argument to apply somewhere else? Like, it's about reason. And yeah, I don't know. I'm kind of going off on a tangent here, but there are things like the four-color theorem. Which says that for any map, you only need 4 colors. Like the map of the United States. If you want to like color in every state in the United States, you only need 4 colors to do that without 2 states looking like they combined into one. And this was proved by computers, I don't know, in the 80s. I'm guessing. I have no idea exactly when, but that is considered a very inelegant proof. It just checked like thousands of cases. It just like did a bunch of calculations and then said, yep, it's true. And that's kind of cool, but it doesn't lead to new questions. It doesn't lead to new theory and understanding for like why it's true. And coming back to this, induction is a great example of something that like you can calculate and show that some math statement is true, but it doesn't really yield any kind of intuition or understanding for why the thing should be true. It's a way to get it done, you know. And contradiction's kind of the same way, but like it gives a little bit more intuition than induction, and then construction is even more so. Like that construction is quite a bit better. Yeah. All right, let me read chat. Ooh, yeah, man, totally. I agree that chasing. So you said proofs are my favorite part of math, and it's not close. Yeah, agreed. Math is proofs. Like I feel everything before proofs is calculation, like computing, like computer science. I mean, computer science is different. Computer science is math, but it's like computing. Before proofs, math is calculating, and that's different. I agree that chasing it in the way that we currently are will never get there. I don't know. I think we are on a very good path for building ChatGPT to do great things. I don't know. Yeah, it's a philosophical argument. Can one replicate exactly the same human consciousness and brain which does feel things like beauty? Can you replicate the same thing in an AI? I don't know. I don't know. I think smarter people than me have argued about this for a long time and have not come to an answer, so therefore it's not worth my time unless I want to contribute to that field of argument and chess. All right, local maximum, etc. I don't think we're near a local maxima. We're still on the steep part of an S curve. We're still like the current methods that we're applying right now. I think that there's a lot more gains to be made just throwing more compute at the machine. It's still getting way better. I do think AI will have some more revolutions that change how it works in the next few decades. Let me try to pull up chat on so that the future viewers can see how intelligent your comments are and how valuable they are. Thanks for stopping by, old man silencer. Let's see. Oh, this is a huge version of chat. All right, let's do it. Let's see. Did that work? Yeah. Proofs. Agree that chasing it, we will never get there. Something or other. Four-color theorem. Yes, four-color theorem has been proved. Exactly. But it hasn't been proved in a human way. In the way that I'm trying to describe human way. We've shown that four-color theorem is equivalent to about 2,000 cases or something, and then a computer crunched through terabytes and terabytes or petabytes, I don't know, terabytes of calculations, and then just checked every single one of those cases. So that's kind of like it's kind of like another type of proof method, like proving something by cases, like case analysis. And that works, but it's like somehow less elegant, it's less like satisfying than some kind of deeper truth or meaning or something, like constructing. If you could construct, if I give you 4 pens and you can somehow show me that you can construct any map out of those 4 pens, that's incredible. That's different. So, yeah. Let's see. Where are we? I think AI will have some more revolutions that change how it works in the next few decades. Oh, yeah. We're not at the final architecture. Like, architectures are still improving, but right now it's still kind of just throw more compute at the thing, ask it the same questions in a loop a few more times. I think when we get into anything that is innate in nature, it gets real dubious real quick. Absolutely. Yeah. Math people get there for different reasons. Sorry, I tend to get you into that often, like into a tangent. Yeah, I always enjoy chatting with you, dude. It's always fun. Four-color theorem has been proved, yes. Boiled it down to thousands of cases, yeah, exactly. Well, kind of some of those methods are used in topology and how they show that a large set can show self-similarity to bring it out to more cases. Ooh, I don't know. I did not follow that. I enjoy calculation too. Calculation is nice. It's fun. And it's super useful. Like, you can actually, build a bridge or something if you do calculations. And I love bridges. So, calculations are great. But, when I want to play chess, sometimes I do complicated calculations, but really I reach for a proof. If I want to have a fun game of chess, I don't think we're at a local max. I think we'll get to a local max that doesn't understand aesthetic. Oh, yes. Agreed. I agree with that. We will get to a local max that doesn't understand aesthetics before we get further, and maybe there's some sort of breakthrough that can get to that next level. Yeah, maybe. It's less satisfying, but it's not less valid. Perfect point. It is not less valid. Any of these methods of proof are valid. You will get an A+ on your paper if you use any of those methods, and you know what? You might get more done if you just prove things a straightforward way, or your future teammates might thank you more if you don't come up with stupid, overly elegant, overly complex answers for everything. Sometimes it's way better to just do the simple thing. And again, this argument about which one is better, that is aesthetics. That is aesthetics that, you can come up with counterexamples all the time. You can, you can't really say with certainty that one of these is ever better than the other. Yeah. Calculation is intensely practical. Exactly. Are you a chess player? No, barely. I'm not very good, but I'd like to be. I've played here and there, after Queen's Gambit, so many other people. I got into chess for a little while. I played a tiny bit when I was young, but I'm not good. I would like to get good at it, though. But it is one of those things where it's if I'm going to learn games and I'm going to master and practice games, is chess the one? I feel like I'd rather play Go. If I got really into a deep single game, I think I'd rather get into Go or poker. I would rather get into poker rather than either of those. But Go, I feel, is a little bit ahead in the abstract, perfect information game category. Poker is ahead, probably, obviously in the, randomized, with some amount of luck. There's, a cool theory about game design. But more than either of those, I think that I would prefer to, more than Go or poker or chess, I'd rather just learn a lot of games, at a more superficial level, and be able to play, 100 different great games. Yeah. I had a professor that graded me down for being lazy on a proof once and just showing cases. He only took off 2 points, but I was being lazy. Okay, there can be times where you might have been lazy. If there can be times where you prove exactly, I don't know, that something is true for the number +1, and then you show that it's also true for the number n equals -1. And maybe you could have just shown that when the absolute value of n is 1. If it's really obvious that you used up 5 reams of paper doing the exact same case all over again, I think I would mark you off too. there are definitely times that that a proof is less valid than another, but only to a minor degree. Like, you know, I'll take off 2 points off of your paper, not give you a C because you made this kind of mistake or something. Yeah, I thought so. Yeah, you're a fairly strong chess player. I remember you mentioned that once. Go is more elegant, but also not deep enough. Ooh, fighting words. You think Go is not as deep as chess? I don't know. I mean, I've played a little bit of Go. I love Go. I've probably played as much Go as I have chess. I don't know if it's not as deep. I mean, is it just that it's just a bigger board and that's why it's more complex? It's complex. I don't know. What do you mean by deep? Go is more deep than chess. Okay, that's my intuition too. So I don't know what you meant by it. Go is more elegant, but also not deep enough. Chess is far more shallow than people think. Go is just also shallow. Oh, okay. So you're introducing the idea of another game that's like the perfect level of deepness for you. For me, it's Netrunner. Android Netrunner, to just like take a random aside here, Android Netrunner is the perfect game. It's so beautiful. Ooh, you play both. That's cool. We should do a Go and chess stream sometime, and you teach me a little bit. You like kick my ass in both of those. That's really cool. I didn't know that you play them both. All right, let's get back to math. Or I mean, we can keep chatting while I copy Velleman's proof. Like, why don't we do that? I want another color. I want like a purple or something. Yeah, there's a purple. Why don't we use a purple? Yeah, I mean, I would love to get good at some of those games. It's, I only have enough space in my life for a couple of deep hobbies. For a while, modern designer board games was my deep hobby, but it's been a little bit. So I'm choosing purple because this book is purple. It's nice. It's like a nice shade of purple. And all right, there's a lot of words in this. Yeah. I wouldn't invest the time again. That's what I've heard. That's what I've heard from other people who have gotten good at chess. They're like, I wouldn't do it again. I wouldn't do it again. It's like, my understanding is that you have to like really, like pretty quick into chess, you have to start memorizing openings. And it's like, just a lookup table, like knowing what the standard openings are. That's pretty boring to me. Like, I don't really feel like just like memorizing a ton of openings. Do I have another chat window thing? I don't. Oh well. All right. You are off screen now, but I can still keep chatting with you. And people can see like the live chat replay anyways. Proof. Let's copy this verbatim. Suppose there... Okay, so Velleman also takes the supposition method. Suppose that there are only finitely many so it's pretty similar, but it's going to be like a little bit more perfectly rigorous and typeset and like organized English sentences, because Velleman's not doing it on the fly the way that I am. Let this be a list of all prime numbers. A little bit of repetition there that I don't love, but let M equal P1, P2. I would have liked the inset, like center this part. It's really important. Yeah. I don't love it. Note that M is not divisible by P1. Interesting. Since dividing M by P1 gives a quotient of P2, P3 Pn and a remainder of 1. Similarly, M is not divisible by any of P2, P3 Pn. Okay. And then new paragraph. We now use the fact that every integer larger than 1 is either prime or can be written as a product of two or more primes. Yeah. We will see a proof of this fact, in chapter 6, see theorem 642. All right, so perfect. I caught that as well, and I kind of called this out. You do need this assumption, which is basically the fundamental theorem of arithmetic. I took that as an assumption. Oh, okay, I don't want to do the self-criticism right now, or the reflection on this. Let's just finish the proof. Okay, you can get very far with a limited set of openings. Okay, fair. On your side, or can you get far on analyzing somebody else's chess openings? Like, title of this book it's incredible. This book is very good. It's called How to Prove It. And if you follow along, we're going to be working through this book. Get it. Someday I should set up an affiliate link and make a penny every time somebody buys it. Because this channel is going to be blowing up, y'all. Everybody in the world's going to be buying Velleman's How to Prove It, and therefore I can make a tiny bit of money, 1 penny at a time. All right, see that theorem? Clearly, M is larger than 1. So M is either prime or a product of primes.
Suppose first that M is prime. Note that M is larger than all of the numbers in the list P1 ... Pn. So we've found a prime number but this contradicts, okay, this is long, but this contradicts our assumption of all prime numbers. Final paragraph. Now, suppose M is a product of primes. Let Q be one of the primes in this product. Then M is divisible by Q, but we've already seen that M is not divisible by any of the numbers in this list, by any of the numbers in the list P1, P2, ... Pn. So once again, we have a contradiction with the assumption that this list included all prime numbers. Okay, finally, since the assumption that there are finitely many prime numbers has led to a contradiction, there must be infinitely many prime numbers. Okay, and he uses a box. QED. I'm going to use the word boom. Mic drop. All right. I don't know, y'all. I don't know. I mean, I didn't, coming back, I feel like I didn't take, maybe I wrote sort of as much as he did, but I think his gender is he, him. Pronouns, I mean. But yeah, OMS. Yeah, you should throw it in your cart. Or you could just wait until I slowly write down every single exercise and theorem and proof. It's going to take a very long time, but you could just get the little sneak peek through this channel. Hope to see you here. It's a great book. I mean, if you do get it in your Amazon cart, if you're interested in proofs, you want that book. And I think that Velleman is like 35 or 40 USD or something. But these Dover books are beautiful. These are fantastic. Get this one too. This is the main book that I'm using for this number theory series. And I think that this one's like $15 or $20 at most. Dover books are incredible because they're all like cheap reprints of old classic math texts. Yeah. So these are the two books that we'll be using in this series. And if you're interested in proofs, those are my main two proof-based books. How to Prove It by Velleman, and then Number Theory by Andrews. One thing that I enjoy about puzzle games is solving the puzzle and then watching someone else solve it differently. Yeah, me too. That's what I like as this structure is forming in this channel. It's like, here, I tried my own attempt, and now we're going to compare it to somebody else. And there's just like ever so slightly subtle different things. I just think that like Velleman really wrote in every little detail. He also presented it as a proof by contradiction when you can prove, you can restate things. Like I started out calling it a proof by contradiction as well, but really you can reformulate this as a construction, I think. But yeah, like if you take out that first sentence, like mine fits on one iPad screen. And I think that there's just something to be said that like giving a slightly more terse explanation at times is more clear for me, and I think for a lot of people. Because like when I see a long multi-5 paragraph proof, 1, 2, 3, 4, 5, yeah, literally 5 paragraph proof, like my mind starts going like, I might not be smart enough for this. I don't know. That's a lot of words. I might not be ready for this. I might have to drop this class or something. Like it makes it like filling in every detail is like has the right intention. I think it's like want to make sure that people who buy this book, like if they need every detail filled in, that they're not lost. But like in the process, filling in all the details can make something less clear, I think. It can make the audience less engaged, I think, because they're not filling in the details themselves. And like, again, thinking of aesthetics of proofs, like this might be one sentence in some of the other books that I have. And it, like Lang or Sayre might literally just write down, consider this, period. Proof. Consider this. Like it would literally be a 2-word and 1 formula sentence as the proof in another book. And then the implication is it's an exercise for the reader to fill in the details, but think about this. Like, that's too far in the other direction. And so books are written with different audience members in mind, and the same theorem will have a different proof in two different textbooks. I think it'd be cool to see, how does Andrews prove this? And something I loved about this book when I was flipping through it, he doesn't prove this until like halfway through the book. Usually this is like the first theorem. It's like one of the very first theorems for a lot of people, or for a lot of books. But he doesn't prove it until like way late. Like after quadratic reciprocity. Like usually you see this way before that. Where is it? All right, let's just use the index like a smart person would. Euclid. Oh, dang it, it's not in the... What? Infinite products, infinite series. What about primes? What? It's like not even in the... I know I saw it when I was flipping through this. That's so weird. Infinitude? It's like not even in the... it's not even in the index. Okay, where is it? Where is it in this? I'm not going to write it out. I'll just pull it up on camera. I just have to scroll slowly through this book. Residue systems, linear congruences, Fermat theorems, Chinese remainder theorem. Might be back there. Arithmetic functions, combinatorial study, Mobius inversion formula, primitive roots. I remember seeing it and just being like, whoa, it's like way late into the book. Elementary properties. Okay, wait. It might be in this one. Oh, yes. Here it is. Chapter 8, Prime Numbers. We have not yet established the existence of infinitely many primes, page 100 in this book. We have not yet established the existence of infinitely many primes, a problem that is easily settled with Euclid's elegant proof. Theorem 8.1, limit of pi x equals positive infinity, that is, there exist infinitely many primes. Yeah. All right. So the reason that Andrews doesn't prove it is the same as where is this note. We will see a proof of this fact in this chapter. See that theorem. So I also kind of cheated a little bit with this. Like you do need the unique factorization of numbers. Unique factorization, which is the fundamental theorem of arithmetic. You really need that to prove this theorem. And so Andrews doesn't do this theorem until after he's already proved that fact. But here is, just so y'all see it, it's like the equivalent. Why don't we get the bigger screen here? All right. So it's the equivalent proof is just this one paragraph. Limit pi of x means the number of primes less than or equal to x. There exists infinitely many primes.
And so it's way shorter. Assume that there are only finitely many primes. Then construct this number. Clearly, if we divide m by any of them, then the remainder is 1. Thus, by our hypothesis, we deduce that m has no prime factorization. Since this contradicts the fundamental theorem of arithmetic, the only possible conclusion is that there are infinitely many primes. So it's like way shorter. Way shorter. Yeah, like I think a lot of people get frustrated when they gloss over some of the logic. Yeah, if you fill in every detail, you can get frustrated and like gloss over it. Yeah. Or seeing what parts they struggle with and how that's different than what I struggled with. Yes, that's like a big concept of this whole stream. Like, because so far things have been straightforward for me, but I will be getting stuck many, many times. If we pull up chat again. I appreciate writing it fully out. Yeah, it was a lot. The proof is left as an exercise for the reader. Indeed, that is such a horrible phrase. Like fuck you. Like, I do need the details here. And that's one thing that I wanted to criticize, because this is a nice proof for like an intro to proofs. But I did want to criticize Velleman on this word here. Like, clearly. Like, don't use the word clearly if you are trying to give an intro to proofs and you are trying to fill in all the details. Don't use the word clearly. Like, this sentence would have worked without that word clearly. If I take chat off for a second. This sentence would have worked without the word clearly. Like, so it's just like slightly demeaning to the audience. Like, if you don't see this, you should drop the class. Is how that comes across. Like, you can literally just say m is larger than 1, so m is either prime or a product of primes. And then it's not, yeah, like these words, like clearly, obviously, details are left as an exercise, those sorts of things have caused a lot of math trauma for a lot of people out there. Proof is trivial from here. This is a pretty foundational proof for most things. Taking it as an axiom isn't that unreasonable. Yeah, I mean, I don't know if you meant the prime factorization or if you meant, I think you meant infinitely many primes. I wouldn't ever take infinitely many primes as an axiom because it's a nice, elegant proof that doesn't require that much. Like, you need the idea of factorization. But what I did was I tried to motivate that a little bit. I tried to define prime this way as like I wrote it down here as the definition of prime. Like, I don't think that, yeah, so, like, I said that, or I wrote that down, and then I also verbally said, like, remember that we're thinking about acorns, okay? Like, we're always thinking about acorns. Every time we're multiplying things, we've got 5 rows and 5 rows of 4 acorns. And you just gave me a bunch of acorns, and I want to put it into a neat little box, because I just like things when they're like a nice, neat, straight lines. Is the only type of box a long box? 1, 2, 3, 4, 5, 6, 7. Like, the only type of rectangular box that I can pick is one with 7 in a row, or is there, like, a number of rows and number of columns where the two multiply together? Like, I think that this idea, like, where we're all motivated to organize
acorns in a nice little grid, that you can take as an axiom, I think. Like, you can kind of take that as an axiom of, like, the product of two numbers, and that, like, that this one is the only option. I don't know, maybe you do need the fact that there's only one representation of a number, that there's only one unique factorization. I think you need that. I think that's why these proofs really clearly call out that you need is either prime or can be written as a product of two or more. I think I'm missing something right now. I'm missing something, but here is the really filled in details version, and it works. It's good. Not the prime proof. I was referring to the fundamental theorem of arithmetic. Yeah. I think that makes sense. And if you're doing a proof-based intro to proofs course, I think that it would be okay to take that as an axiom, because it's fairly hard. It's not easy to prove the fundamental theorem of arithmetic. That takes a little bit of math maturity to get there. But if you're teaching proofs to 8th graders, I think you can assume that as an axiom, and then you get a wonderful, beautiful, proof from the book, quote unquote, with this as the canonical example of a proof. So this is we are ranting a lot longer than I planned on, but that's always what happens on this stream. Let's do one exercise or two. I liked that Velleman explicitly gave an example here. One of the exercises, we're going to do this one right now, so we can see how Euclid's proof is really a constructive proof. Rather, like, it doesn't need to be a contradiction proof, I think. If I understand correctly, unless I'm missing something. Euclid's proof of infinitely many primes. Oops. Let's do that one more time. All right, so now it all fits nicely. So here's this exercise. And it's all related to this thing. We know that. Proof of Theorem 3 gives a method for finding a prime number different from any in a given list of prime numbers. And again, that is what Euclid did. He said, this is an algorithm to find another prime. Like, from any set of primes, here's an algorithm so that you find another one. So, part A. Use this method to find a prime different from 2, 3, 5, and 7. So I'm going to use capital N again. I guess, well, whatever, let's do it. Let's consider the number 2 times 3 times 5 times 7 plus 1. Okay, so we have 30 times 7. 30 times 7 is 210. So then this sum is 211. Okay. By the proof that we just saw, we know that it's not divisible by 2, 3, 5, or 7. So then the next number to ask, next numbers that we can consider are Pn plus 1, maybe being, well, here's prime 1, prime 2, prime 3 that we were given, prime 4. I'm going to call this one prime 5 that we can check, being 11. Does that one divide to 11? If I were smarter, I'd know that quickly, but I'm not. So 101, no, right? Yeah. So 11 does not divide to 11. 11 has remainder 2. 19, remainder 2. Right? And just so that we're all very clear, this notation here means that 211 equals 11 times 19 plus 2. Here's like the factorization or the division algorithm written out for 211. All right, so 11 doesn't work. What about the next prime? Does 13 work? Does 13 go into 81? If it did, it would be by 7, and that doesn't work. 6, that would be 78, remainder 4, right? So 211 is 13 times 16 plus 4. I'm writing these out because later on, like, we'll be writing more linear equations like this, and so it's good to just see how that works. All right, what about the next prime? 17. We kind of just already know that these are primes, and so we're sort of assuming things as we go, but nope. Oh wait, nope. Okay, so that's remainder 7. Oh my god, okay, so based on this algorithm, we know that we should be able to find one, and where is it? 19 into 21 one time. One time. Where is it? This is an annoying problem. I don't feel like this is the best example. 23? I mean, we could just use a calculator. We could ask ChatGPT. 5 doesn't work, but it's pretty close. 5 times 23 is 215, so 23 doesn't work. This is an annoying problem. 27 is not prime. 29 is. What is this? 6 times 29 is 180 minus 6. Yeah. Oh, wait. 7. What is 7 times 29? No, 7 times 29 is not going to work either, right? Let's ask ChatGPT. This is getting boring. This is getting super boring. Alright, let me catch up with chat. You've got a couple things. Proof that 1 plus 1 equals 2 is super not trivial. Yes, you're referring to Bertrand Russell's Principia Mathematica, and it takes like 700 pages to prove 1 plus 1 equals 2. And that's if you just go way down the rabbit hole of trying to go down the rabbit hole of foundations and try to prove all of mathematics on like simpler and simpler and simpler things. And then Hilbert's put a lot of people to task trying to formalize mathematics, and then somebody named Gödel showed that that was a giant waste of time and that everyone should stop wasting their lives. So there's a fun fact about Gödel and completeness theorems. We're getting so close. 211. We're missing something here. Because if it is divisible by something, it should be the square root of 211. The square root of 211 is going to be less than 15, right? Yeah, because 15 squared, I think, is... Am I wrong? 15 squared is 225. Yeah, that's what I thought. Alright, so we went way too far. Because if there is a prime that divides 211, I think that that's a point. I think that that might be the point. If 211 is prime, isn't it? I'm glad I noticed. Now, I feel like we should have checked, or we should have realized that a little bit earlier. But is theorem 3 in this book the same one that I was looking at, or is there a follow-up? Nope, it is that one. All right, so I think that 211 is prime. Let's find out. Let's ask ChatGPT. Yeah, 211 is prime. That's what I thought. So if there was a... If 211 equals AB for A and B, for A greater than 1 and B less than 211, then B needs to be less than or equal to the square root of 211, because otherwise... Oh, wait, no. A needs to be... Oops. A needs to be less than or equal to the square root of 211. Otherwise, for any x greater than the square root of 211... x squared is going to be greater than 211. I hope that makes sense. So, we should have been done here. 11 does not divide 211, and 13 doesn't divide 211. 11 not dividing it, and 13 not dividing it, and 17 being greater than the square root of 211 proves 211 is prime. Cool. All right, so that problem, I was immediately assuming that we were going to find a prime not equal to 211. But that wasn't true. Use this method to find a prime different from 2, 5, and 11. Hey, how's it going, Jeffrey? How are you, man? How's it going? All right, so P1 is 2, P2 is what was it, 2, 5, and 11? Yeah. And P3 equals 11. Then the construction is 2 times 5 times 11, which is going to be 110, plus 1. Oops. 110 plus 1, 111. 111 is not prime, and I can tell you that because I recently relearned that 3 divides a number if and only if 3 divides the sum of the digits of that number. And that could be seen by the base representation, not 3, whatever. Doesn't matter. Like each power of 10 in the basis representation of a number is 1 mod 3. So then 3 divides the number if and only if, each coefficient times 10 raised to the n is congruent to the coefficient. And then if all of them add up to a multiple of 3, then 3 divides the original number. So I know, just looking at 111, that 3 divides it. So what is that number? Well, 3 times 33 is 99. So then 3 times 37. Yeah, it's going to be 37. But more slowly, 3 goes into 11 3 times. And then 3 goes into 21 7 times. So 111 is 3 times 37. So we got 2 new primes this time, I think. Well, I don't know if the other one is prime. I think it is, but the theorem doesn't prove that. The theorem proves that we're able to find another prime, and 3 is. Yeah. 37 also is. But the theorem only proves that we're going to get at least 1 more. This was like a bonus prime. Cool. Hey, this has been fun. We've gotten a bunch more views and likes in this stream than we have in other recent ones. That's dope. All right, so we finished one Velleman exercise. I'm about ready to call it a day for today. So we did Velleman 0.3. Tomorrow, I think we'll be back to number theory, although this was number theory too. I haven't written Velleman into my little table, exercises tables yet. Where do I want to write? Let's see, leave some space for Andrews in the other one. Velleman 0, which is introduction. I think we did problem 3. Which problem was that? Yep, 3. We did problem 3. I feel good about it. We don't have to revisit it for a while. I want to go ahead and solve one quickly from section 1.1 and 1.2. Because I saw that some of those coming up are not too bad. I think that we can just like quickly go through these, and I'm going to explain as I do it a little bit more briefly. Okay, what's a fun one? Let's do this one. And let's do a truth table too. Let's do the first truth table. All right. So we've got a couple of fun little problems. I'm going to just kind of briefly say as I solve them a couple of things. This symbol means not. This symbol means and. And so this sentence means it is not true that I will buy the pants and I will not buy the shirt. So this is like the long statement. It is not true that I will buy the pants and I will not buy the shirt. That's like kind of a double negative convoluted thing, and you can see the double negative right there. I will not buy the pants and I will not buy the shirt. I will not buy the pants or I will not buy the shirt. Cool. 1.2.1, let's make a truth table for this thing. So if we have some statement P that's either true or false, I'm going to use 1 equals true and 0 equals false everywhere. So if both are true, or if the first is true and the second is false, or if the first is false and the second is true, or if both of them are false. Those are the 4 cases. Then not P, we're going to build not P, we're going to build, we're going to build not P, and then we're going to build not P or Q. I haven't said it yet, but the upward triangle thing is usually means or. I haven't checked the book. I think I'm right. I think I remember that right. I think it's or. Okay, so not P. So you change true values to false and false values to true. So if we invert P, we get 0, 0, 1, 1. And then so the or function is if either one is true. So here, when Q is 1 and not P is 0, then not P or Q is true. In this one, it's false. In this one, it's true. And in this one, it's true. Okay? So, when Q is true, then the thing is true. Or when P is not true. So, yeah. Okay. There's that first truth table. Next one, S, G, S or G, not S. I'm going to write them all out just for clarity. For clarity. Not G, not S, or not G. And then finally, S or G and not S or not G. This is the one. Okay, so what are possible options? 1, 1, 1, 0, 0, 1, 1, 1. I don't know what the book uses. Probably true and false, T and F, but I like zeros and ones. So, or, S or G. It's going to be 1, 1, 1. Oops, this last one should be 0, 0. Not S, we invert the S column. Not G, we invert the G column. 0, 1, 0, 1. Not S or not G. So when either one of these is true, is going to be this. Not S or not G. Now finally, we are comparing this one and this one. S or G and not S or not G. So both values need to equal 1. So in the first case, we have 1 and 0, so it's 0. In the second case, both of them are 1. In the third case, both of them are 1. And then in the last case, they are not both 1. Cool. So there's our answer. Voila, there's the 1. Thank you everybody for watching. Here's a little intro to proofs. My name is the Math Hobbyist. If you enjoyed this, if you're still watching, you must be a fellow nerd like me. Hit the like button, hit the subscribe button. Let me know that you enjoyed this. It means a lot to hear that people are enjoying the series, and that, yeah, that's it. Thank you. Thank you for watching. Thanks for watching. It really, honestly means a lot to hear that people enjoy this. If you want to buy me a coffee, you can go to coffee.themathhobbyist, and I will use that to make more math videos for you all. I drink a lot of coffee, and I immediately convert it into math. That is a classic joke. So, thanks for watching. Have a wonderful day.